Yeah.
See, that's good because they stay in my How would you respond? True, but they're pretty good.
If you work with faculty one time and then afterwards they just start basically.
Better public transportation.
I'm still trying to process how to deal with that. So I worked with Flo over the summer in like the laser lab for.
Okay, please don't forget to use your clicker to check attendance, and you can find your attendance grade on Canvas. If you are actually here, but you get 0 grade, just let me know. I can always enter the missing grade for you. The other thing is that I posted homework 1 last Wednesday, so you can start working on that. It will be due next Wednesday, and you can come to my office hours for help on the homework. It will be today and also Wednesday, Monday and Wednesday from 3 to 5 in my office. It's in the course tag 321. You can also come to the TA's office hour, which is every Monday from 2 to 3. You can come to his office hours first and then come to me if you have other questions. The first homework, there are 3 big problems. The first one is just kind of a review of quantum mechanics. And the second problem is about how we do tensor product to write the Hamiltonian, the many-body Hamiltonian, and then ask you to write a short piece of code on your favorite software to actually find the ground state energy and ground state wave function of that Hamiltonian. And the last problem is about harmonic oscillators and touches a little bit on the second quantization we talked about in the last class. Any questions about the logistics homework? All right. Okay. So yeah, don't forget to use a clicker if you come late. Okay. So today we're going to keep talking about second quantization. In the last class, we basically said that if we have a many boson or many fermion system, here we're going to assume that we either have, say, n identical bosons or n identical fermions. We're not going to talk about the mixture of the two for the scope of this class. So in this case, we can actually describe the state of them using this many-body Fock state. So this many-body Fock state is also a basis state. It's similar to how the Fock state for harmonic oscillator can be used as a basis for the Hilbert space. And this basis state is denoted by N1, N2, etc. And each of this, the quantum number N here basically denote that we have N1 particles. Again, these can be either bosons or fermions. You have to specify whether you have bosons or fermions in your system first. N1 particles in state 1. In some state 1, I'm just going to call it precise 1. And similarly, this is N2 particles in state precise 2, and so on. And these states, these precise states, so precise 1, precise 2, and so on, they basically form an orthonormal basis for a single particles state. So suppose you only have one particle, and then we can always find some basis, orthonormal basis. There can be infinitely many of them because we're talking about a particle that's moving freely in space. Even for harmonic oscillator, the Hilbert space dimension is actually infinite. So we can just choose some orthonormal basis, and usually we choose the energy eigenbasis because those basis states will be stationary states. So if you put the particle there, it will actually not involve. The wave function only picks an overall global phase over time. So it's basically a stationary state. So you pick these bases, and then if you have n particles here, then you basically specify how many particles are in each of these eigenstate or each of this basis state precise k here, and then you basically list these numbers. If the number is 0, usually we just don't list it, just omit it. But anyway, but that's basically how we write this many-body basis state. We call it many-body fog state. So this basis state, we can also think about this basis state as the state that's created from vacuum. So we talk about this relation between this basis state N1 and N2 from the vacuum. So what we are going to do is basically we apply the creation operators C1 dagger to the power of N1, and then C2 dagger to the power of N2, and then dot, dot, dot. If you have more, you just keep adding it to the left, and then this will act on the vacuum state. So this is the vacuum state, basically with no particles. The other way to say it, this is a state where N1, N2, and all the other are equal to 0. So it's a state where there is no particle. And then you basically apply the creation operators N1 times on the vacuum state, and then the creation operators C2 dagger on, for N2 times. So, and then you will get to that many-body fog basis state. Okay, and one thing we said about this is if we have bosons, then the order of this creation does not actually matter, because these different CKs actually commute. So if you have like, for example, a CK and a CL, if you look at the commutator of this, it's actually equal to 0. Sorry, I got a cold last week. I'm still coughing a little bit. So for bosons, the order of the creation does not matter, but for fermions, actually, it does matter. Sorry. So for bosons, this means I can swap the order of these two creation operators. So you have a K and L, assuming K is not equal to L. Then you can swap the order of this creation. You can also swap the order of the creation here. It doesn't really matter. But for fermions, it kind of matters, because we have this anti-commutation relation. What that means is this is actually equal to the negative of this. So this means for fermions, if you create the particles in a different order, and then you could actually get a sign difference. And the sign difference is actually important, because if you have a superposition state of different basis states, then you're actually getting a relative sign between different basis states. And to avoid any sign ambiguity, we basically fix this order here. So you can see that in this creation, the string of creation operators, we always first create the first eigenstate. The C1 is always to the very right, and then you have C2, C3. This is just a convention, but we're just going to fix this convention to make sure we don't have any sign ambiguity. So the other thing I want to talk about is, so these bosons and fermions, we define these creation operators kind of more or less abstract, and you can think about that. This whole second quantization is basically built on the fact that we have these creation and annihilation operators. And this is also kind of the idea behind quantum field theory. In quantum field theory, you can think about every elementary particle as basically, it's kind of similar to a harmonic oscillator, and you can always just use creation and annihilation operators to describe these particles. They don't actually need to be harmonic oscillators. And for this, I want to show you a brief video of what is quantum field theory. It's kind of related to this idea of second quantization.
The framework in which quantum mechanics and special relativity are successfully reconciled is called quantum field theory. It is based on three basic principles. Two of them, of course, are quantum mechanics and special relativity. The third one, which I wish to emphasize, is the postulate that every elementary particle are point-like vibrations in quantum fields. Remember the wave-particle duality? Mind-blowing, right? Yeah, forget about it. In fact, there are no particles and no waves, just fields. Both particles and waves are merely two ways in which we naively interpret quantum fields. There is one field for each type of particle. So one field for all photons in the universe, one field for all electrons, one field for all muons, and so on. And these fields exist everywhere. To extract a particle from a field, you need to give the field energy. If you give it enough energy, the field will go to a higher energy state. These states are what we interpret as particles. The point in the field where you gave it energy will look like a particle. And as the energy propagates through the field, it will look like the particle is moving. Some fields require more energy than others in order to create a particle. The amount of energy is proportional to the mass of associated particles. For example, a Higgs boson. It is much more massive than an electron. So electrons are very easy to create, but Higgs boson, not so much. Here's an easier way to think of this. Think of fields as vending machines. You put enough money in, you get a packet of chips. You put more money in, you get another packet. The money is energy and the packets are particles. So if you have enough energy, you can get as many particles as you want. You can go, for example, to an electron machine, pay some money and get an electron. And then you can go to a photon machine, pay some other amount of money and get a photon. There are 18 such machines that we know of. So according to quantum field theory, fields are everywhere. Particles are field vibrations, and you are awesome.
All right. Yeah, so you can basically think about every elementary particles as some kind of excitations of a field, and then you can always use creation operators to and annihilation operators to describe it. For example, you can actually create electron at a particular position from that electron field. And the fields, you can think about it as basically harmonic oscillators. It's kind of like a matrix. At each point, you're basically getting a little bit of oscillation there, and the excitations of the oscillation, the energy is quantized, and that gives you these particles. Yeah, question.
So the energy required to create a particle from the field is proportional to the mass of the particle.
Yeah, for elementary particle, that's the case.
Right.
Yeah.
Is there, so in semiconductor physics, we talk about like relative levels of band gaps and that kind of thing. Is there a uniform ground state for all of the different fields for different particles, or do they have different ground state level energies?
So for semiconductor, we're not, if you look at the band theory, it's not actually the real particle, it's more or less the quasi-particle.
Right.
Yeah, so, if you're looking at the fundamental particles, these 18 different fundamental particles in nature, those are unique. So those are, it's not like you can use a band theory to describe. So,
Sure, you can't really compare the
yeah, so they're just different. Those are unique. But later on when we are going to talk about the band structure of interacting for electrons or spins, so those are kind of like the quasi-particles. And also, we're going to talk about this very soon. So even if you we're looking at the idea here, we talk about this single particle eigenstate per psi 1 per psi 2. So for each eigenstate, there's going to be a quasi-particle associated with it. So that quasi-particle would basically be, a particle with in that particular state. So it's not necessarily a true particle, but as long as you can, create a quantized energy, right? It's basically like going from, basically just occupying one eigenstate. You can call that a quasi-particle. And the typical example will be a harmonic oscillator, right? You have a mechanical harmonic oscillator, and then the quasi-particle associated with that oscillation, that h bar omega is called phonon. And the phonon is a very typical quasi-particle. It's not a fundamental particle like electrons, but it's just some kind of quantized energy we put to the system, and you can treat it as a particle, just fine. It turns out the fundamental particles behave in almost the same way. Right? In quantum field theory, they're described by very similar things. Yeah. Any other questions? Good one. Yep.
I guess we don't have to go too much into it, but like, what does that mean? Like, fields are everywhere. Like, I've trouble like visualizing that in like energy levels or how?
Yeah, it's
Really pretty.
yeah, it's kind of imaginary. You can even think about just everywhere. For example, electromagnetic field is everywhere, right? So that's one way to think about it. You know, electromagnetic wave is just everywhere. It's even in the vacuum, right? Even if you don't have anything, but the fields are still there. It's not zero. It's not exactly zero because you have these 0 point energy. So it still fluctuates a little bit, but it's so weak that it's very hard to measure because the energy is like very small, right? It's half of h bar omega. Think about h bar is 10 to the minus 34, right? It's a tiny little bit of fluctuation even in the vacuum. So vacuum is actually not vacuum. And one very good example is if you have like a real atom, sometimes if you put it in the excited state, it will decay down to the ground state. And this process is called spontaneous emission. And for a long time, people want to understand how could we have spontaneous emission, right? Because the atom is just sitting there doing nothing. You can put it in a completely isolated vacuum with nothing there. The atom will still actually decay to the ground state. And it turns out the reason is because the atom is actually coupled to the vacuum, and the vacuum electromagnetic field. And the vacuum is actually not the true vacuum. That little quantum fluctuation I was just talking about actually causes the atom to go from the excited state to the ground state after a while. So that's actually something quite real. It's not actually vacuum. Yeah, question.
Similar to why we see like the photoelectric effect, like if you shine a light onto like a metal or something.
That's not quite, because in that case you actually have some light matter interaction. It's not vacuum. Basically the material is directly interact with the laser and exchange energy. Yeah, so what I'm saying is spontaneous emission is like you don't have anything. It's just you just place the atom in the vacuum and the atom will still interact with that and emit an energy. And what it does is the atom goes from the excited state to the ground state and the vacuum will get a photon. It emits a photon into the vacuum.
Right. I guess
yeah.
I meant more so just in the case of just like if you were to see like the surface that you're shining the light on as a field, then you're exciting the.
Yeah, you can think about it that way. You can think about everything as a field. It's just a good way of thinking, because in undergraduate quantum mechanics, you learn there's wave particle, there's this duality. It's kind of paradoxical, right? But if you think about quantum field, it's actually unified, right? A particle is just a quantized excitation of the field, and the field you can of course create a wave, right? Just like a mattress, or just like creating ripples on on a water surface. It's a similar idea. Yeah. Okay. So what is kind of more exotic, which is something that this video didn't talk about, is that there actually exist two different types of field. One is bosonic and the other one is fermionic, right? The bosonic ones is not that hard to understand. It's kind of exactly as the mechanical harmonic oscillator you learn in undergraduate quantum mechanics. But the fermionic ones is kind of exotic. You just can't, right, this field here, you just can't create two particles at the same position. That's just how nature works. There's really no good way to explain why there exist fermionic fields and fermionic particles, but they just do exist. And for fermionic ones, you can't really think about it as a harmonic oscillator, because if it's a real harmonic oscillator, you can put many particles, many phonons in it. The fermionic ones, you can think about it still as a harmonic oscillator, but it's just that you can only put one excitation into that. You can't put a second one there. So that's the way to think about it. And so we briefly mentioned about the commutation relations about these creation and annihilation part operators. So for the bosons, if you're just talking about the same type of particles, so labeled by the same K here, then we have CK and CK Dagger's commutator, so that is equal to 1. So this should be what you learn in quantum mechanics. This comes out of the harmonic oscillators, X and P's. These creation and annihilation operators are made of position and momentum operators, and that will give you this commutation. But in general, if you just have any boson or any bosonic particles, they always have to obey this property. So the CK and CK dagger just talks about the creation and annihilation operators for the same type of bosons, right? And then if you have different types of bosons, so for example, you have like a CK and a CL dagger, so that is also equal to 0, and you can also think about CK and CL and CK dagger and CL dagger. So these are all equal to 0 just because these are creating or annihilating different particles. And from what we just said here, it doesn't really matter for bosons, the order you create or remove them, it doesn't really matter. So this is what these three equations actually tell you. You have two different type of bosonic particles, right? You can create or remove them in arbitrary order. It doesn't really matter. So bosons are generally easier to deal with. And now for fermions, the situation is different. What you basically do is to replace all the square bracket here by the curly bracket, which denotes the anti-commutator. So you will have this equals to 0, and also these other ones all equal to 0. Yeah, so as we just explained here, for example, this last equation means that if you create one particle and then the other, it's going to be equal to the negative of the opposite order, because we know that for fermions, exchanging two particles will give the wave function a negative sign. And in terms of the operators, this basically means if you swap the two operators, you get a negative sign, which also means if you apply these two products of creation operators on any state, you're going to get the negative of that state. And that obeys the exchange statistic we said, which is one of the fundamental assumptions of quantum mechanics. And this also happens when you're like creating a particle L and then removing a particle K. And if you swap the two particles, it's like you first remove a particle in K and then create a particle in L. And that also gives you this anti-commutation equals to 0. So it's all because of that you exchange two particles, you get a negative sign. Question?
So a bit last week you talked about how these relate to probabilities. Are these still probabilities that we're working with?
These are not probabilities, but when you apply these operators on a state, you will get another state. And when you have a state, you can take an inner product with a different state. That will give you probability, right? So you're right. If you just look at the probabilities with an eigenstate, they will be the same because the negative sign will get modular square equals to 1. But when you have a superposition state, then that's going to change the probability when you swap the two particles, right? And probability is something you can measure physically. Question?
And these are not unitary, so you'd have to renormalize after.
No, these are creation and annihilation operators. They're not Hermitian, and they're also not unitary. Yeah,
Okay.
yeah. So similar to, if you remember, for harmonic oscillator case, right, probably if some of you remember that each of the C is kind of like an x plus IP over square root 2. Roughly like that. There's some coefficient there. But if you think about this operator, it's certainly not Hermitian, because if you take the complex Hermitian conjugate, it becomes x minus IP, and then it's also not unitary. Yeah. Because C dagger C is actually equal to the number operator, while for the unitary operator, U dagger U has to be equal to identity. Right. Okay. So the fermions are usually something you need to pay more attention about just because there's anti-commutation. So when you swap the two, you always pick a minus sign. So I have a small question for you, just to make sure you all understand these fermionic anti-commutation rules. So suppose I have 3 different types of fermions. So basically my K can be equal to either 1 or 2 or 3. So I want you to find out which of the following options are actually correct. So the first one is C1 dagger, C2 dagger, C3 is equal to C3, C2 dagger, C1. And then the second one is C1 dagger, C2 dagger, C3. So this is for 3 types of fermions. I have 3 types of fermions, denoted by C1, C2, C3. And then this is equal to the negative of this. And then the choice C is that they're just not equal. This is basically neither A or B, so let's make it more consistent. Okay, so you can think about this. Sorry, there's a dagger here missing. Yeah, the first one is I have 3 of these creation and annihilation operators as a product, and then when I sort of flip the whole order, this is 1, 2, 3, and 10 to 3 to y is equal to each other, and the next one is they got a negative sign. And the last is either positive or negative. They're just generally not the same.
Question.
Yeah, question. Yeah.
There's a dagger on both sides.
Oh, sorry.
Right side, but not.
Yeah, yeah, yeah. That's right. Yeah, it's the same thing. Yeah. I'm just changing the order of the operator. Yeah. And think about this. And then you can use your clicker. I'll add another option of I don't know if you just don't know the answer. But hopefully everybody can at least figure out an answer based on the rules we just talked about. Okay, it looks like the iClicker software stopped working. So I can't see the statistics. I just have to ask you. So how many of you choose A? Okay. What about B? Oh, okay. What about C? Okay, 1. I guess I don't need to say about D. Okay, so some of you choose A, most of you choose B. So B is actually the correct answer. So let's think about this. This is this is an interesting question. So what we need to do is to swap the operators to get to the right-hand side. So let's see how many swaps we need. So the first thing I'm going to do is to swap the 1 and 2. So this is going to give me a negative sign because of the anti-commutator we just talked about, right? So this is becoming negative C2 dagger, C1 dagger, and C3. So this is still not yet equal to the right-hand side. So what I'm going to do is to swap the 1 and 3 here, right? Swap particle 1 and 3. So I'm going to get another negative sign because of that. And that cancels with the negative sign. So I'm going to get a plus sign of C2 dagger, C3, C1 dagger. And that's still not equal to this. I need to do another swap between the 2 and 3. So when I do that, I get a negative sign and then get C3, C2 dagger, C1 dagger, which is equal to this, right? So you can see that I need to perform 3 swaps, and each swap give me a negative sign. Question, yeah?
So can you think of it anytime as just like switching any two gives you a negative, like if you thought of it as like switching 1 and 3, or is that always there?
Yeah, exactly. If you swap the odd number of times, you will get a overall negative sign. If you swap an even number of times, it won't. Yeah, question.
Are you only allowed to swap next to each other? Like, see,
Yep.
swaps?
Yeah, that's right. You can only swap the, well, actually that's a good question. I think you can actually swap, actually you're right. So you can, you're right, you can directly swap these two, right? And you will still get a negative sign. I think you're making a good point. You're right. You can swap between the 3 and 1 directly, and that's actually a shortcut to get this answer. I didn't thought about that. Very good point. Yeah. What's your name, by the way? I forgot. Brandon, yeah, that's an excellent point. Yes, you can just, in this case, I'm actually doing a detour. You can directly swap 1 and 3. Yeah, that's a very good point. Yeah, you can. You can directly swap any 2 particles. All right. Yeah.
Just so I understand, when you say order matters in this case, it's only because of the sign change.
Yeah, it's only because of sign change. Yeah, but the sign is important.
Okay.
Right. Yeah. Okay. Any other questions before we move on? Okay. So the next part is change of basis. We sort of briefly reviewed this in the second class about quantum mechanics. In quantum mechanics, we have the freedom to choose different basis states, right? You can choose, you can move from one basis to the other. And once you change the basis, you're also going to change how we define these creation and annihilation operators. So we need to talk about how the change of basis is going to affect the way we represent these many-body Fock states. So we just talked about that when we define this many-body Fock basis states. It's always that we have some single particle basis in mind, right? We have this psi 1, psi 2, and so on, which forms a basis for my single particles Hilbert space. And then I can specify the many-body basis state using this second quantization notation. So what if I want to choose a different basis states, right? So previously we choose this psi 1, psi 2, choose this basis, and then we have this many-body Fock state denoted by this. So what if now I want to change this basis states to something different? So let's call the new ones phi 1, phi 2, and so on, right? So the key we need to do here is to basically find the creation and annihilation operators for these new bases, right? So remember, so for this original basis, we denote the operator ck dagger as the creation operator. So this creates a particle in basis state psi k, right? So now we change the basis, we need to use a different set of creation and annihilation operators. And so let me denote this by a L dagger. So this creates a particle in basis state phi L. And the goal here is to find the relation between AL dagger and CK dagger. Right? Are there relations between the two? And it turns out that we can actually relate them. And the reason we can relate them is because with the change of basis, we can actually find the relations of the old basis with the new basis by the unitary operator that performed the basis transformation, right? So suppose this basis transformation is denoted by some unitary operator U here. So what that means is that suppose each of this phi of L is denoted by some unitary operator U. So this is the operator acting on the old basis state psi. So actually, we can write it as a neater combination because let me write it in this way. So this is going to be a sum over K, U, K, L, phi K. Right. This UKL here is the matrix element of this unitary operator. As we said before, for the unitary operator U here, you can use either the old basis or the new basis, and they will be given by exactly the same matrix, just because that unitary operator denotes the transformation. And then you can always expand any of your new basis vector as a linear combination of your old basis vector, and the coefficients are given by that unitary matrix, right? So once you have this, it's actually not hard to figure out what the relation between these two creation operators. So in this case, we can basically see that AL dagger is just equal to sum over K, U, KL, CK dagger. So it actually follows exactly the same equation as the basis transformation. And in order to see why that's the case, we can simply note that we can apply the AL dagger operator on the vacuum state. So this is a state with no particles. And this will exactly create the phi L state. And similarly, CK dagger applying on the vacuum state will create the state phi k. And if you use these notations, you can see that these two are exactly equal to each other, right? Because if this equation holds, and then you can apply it on the vacuum from both sides, and from left-hand side, it gives you phi L. From the right-hand side, you get exactly that summation on the right. So that reproduces the basis transformation. Right? And these two equations are just the definition of the creation of. I just wrote it in the words, right? This applying on the vacuum means you create one particle in the eigenstate per psi k. So that just becomes the state per psi k, because we just have one particle there. Okay, so this is the basis transformation. So in your next homework, I will ask you that using this basis transformation, you can show that the AL and AO dagger, they also satisfy the commutations we talk about for bosons. So they will satisfy these equations. So this basically means if you have a unitary transformation between the two bases, and then if the original ones are bosons, then you also end up with bosons. It's kind of more or less obvious, but it will actually conserve the commutation relations. So the change of basis itself will not affect the type of particles. If you have bosons, after the change of basis, you will still get bosons. You won't get fermions for sure. All right, any questions? Okay, so at this point, you probably don't see the benefits of doing the basis transformation. It's more like a tool I want to mention first, but we'll soon see that the change of basis is actually very important. So it's kind of similar to what we're doing in undergraduate quantum mechanics. You somehow, a lot of times you want to change the basis such that the operator you're interested in, often the Hamiltonian operator, becomes diagonal. And then in the second quantization picture, we often need to change the basis such that the Hamiltonian also becomes diagonal, not in the sense of a matrix, but is diagonal in terms of the creation in annihilation operators. So we'll talk about what that actually means very soon in the following. Okay, so next we're going to talk about second quantization form of operators. Okay, so far we've been only talking about the second quantization form of the many-body state, right? We talk about these many-body Fock bases, and then for any other state, you can always write it in terms of a superposition of these different basis states. So basically, these states, if you have a superposition of them, you can represent any state of, say, n-identical fermions or n-identical bosons by using a superposition of these basis states. So now let's switch to the operators. How can we actually represent the operators in this second quantization form? Okay, so let's start with the simplest case, single particle operators. So a single particle operator basically means this operator only acts on basically is only a property of that single particle, right? You know, an operator is basically some physical observable. If that physical observable only depend on the property of just a single particle, individual particle, it doesn't involve like interaction or any kind of coupling between two particles, then we call it a single particle operator, right? For example, you can think about it as the position of each particle, or you can think about it as the spin angular momentum of each particle. So if it's just regarding the properties of one particular particle, it's a single particle operator. Okay, so if it's a single particle operator A, and if the particle is for the ith particle, we can denote it by AI, right? But since we have a system of n identical particles, if you are looking at a particular property, and that property should be basically for every particle, because these particles are indistinguishable. They're all together. So when we're talking about a single particle operator in the many-body system of n identical particles, then what's going on is this particle this operator A, we need to perform a sum. So I call this a curly A, which is a many-body version of it. So this should be a sum over all the AIs, the individual particles, right? Because they are indistinguishable, so you should apply this to everyone. And what that actually means is if each of the AI here is kind of like this abbreviation we talk about when we are talking about the spins. So the AI here actually stands for the identity of all the other particles, but with an operator A on the ith particle, and then you have identity elsewhere. So this is what the AI stands for. If you're really talking about an operator that's acting only on the Hilbert space of the particle I, then what you basically do is to do a tensor product with the Hilbert space of all the other particles. Right? And when you have n identical particles, you should do a sum of all of this, and then what you're going to do is do a sum of all these AIs. So you have these tensor product. So this is what sort of a single particle in a many-body system actually looks like. Right, so to give you an example, we can, for example, talk about the potential energy. Suppose we have a Vx. So this is applied to all identical particles. So basically, you put n identical bosons or fermions into this potential well here, right, denoted by this Vx. And then you ask, what is the potential energy of these particles together, right? And that falls into this category. So we can denote this by this curly V here. And this curly V here is going to be basically a sum over I of Vxi. Right, this makes intuitive sense. This is a total potential energy for these particles together. We just add the potential energy for each one of this. And if you really think about this mathematically, each of this term actually is going to be like identity on all the other operators, but then you have a Vxi, x is a position operator on this particular ith particle. And then you sum over everything together. So this at the end is going to be an operator, right? Because in quantum mechanics, potential energy is also an operator, right? It's an operator in the Hamiltonian.
What is
Yep. Sorry?
What is I again?
I just denote the ith particle. Right? It's a label of the particle. Okay, so you can also see that you can use this way to do it, but it's kind of a little bit inconvenient because you have to do a sum over I of these different AIs. And then how about we express this using the second quantization picture? Then we can actually do things a little bit easier. So let's think about this in terms of the second quantization picture. The idea, so basically we have two steps here. So the first step is we want to represent the single particle operator A here, so this particular A here, using some eigenstates. So typically we choose A's eigenstates, so denoted by per psi k. So what that means is A acting on per psi k is equal to lambda k times per psi k. So this A here is assuming you only have one particle, and then that AI, or that curly A, is just going to be reduced to this operator A here. So this is the single particle version of this. Okay, so now the next thing we can do is introduce this second quantization notion. And then what you can actually see is that we can introduce this CK dagger operator. So this creates a particle in state per psi k as before. And then we can see what this curly A here, so this operator we're doing here, so what does it do on the many-body Fock state, N1, N2, and so on. Right, so this N1, N2 we denote N1 particles in state per psi 1, N2 particles in state per psi 2, and so on. right? And this is actually not very hard to figure out because this is a sum over all the particles. And what's going on here is that because A acting on the eigenstate gives you lambda k, right, for the particular state per psi k. And how many particles do you have in the state per psi k? We have nk particles, right? We have n1 particles in state per psi 1, n2 particles in per psi 2. So every time we apply this operator A on a particular state, we get an eigenvalue of lambda k. But this is a sum of it. So if you have nk particles in that eigenstate, we will have an eigenvalue, basically the prefactor that is nk times lambda k. So what we're going to get here is actually a sum over k, nk times lambda k. And because we're using, so this n1 and 2, this is kind of like a basis, it's an eigenstate for the operator A here, so we are still going to get the same state, many-body Fogg basis state n1, n2, and so on. So this is the relation between the two. So it takes a little bit of thinking of understanding what's actually happening here. Right? So the first you want to understand is A acting on per psi k is equal to lambda k. And then you can think about that this actually denotes there are many particles, so n1 in per psi 1 and 2 in per psi 2. And this curly A here is a sum of this individual A, so you take the sum of this. And the easiest way to understand it is to think about A as the total energy of the system. So for example, you can think about this A. So suppose each of the AI is just equal to the Hamiltonian for a particular harmonic oscillator. So we think about, let's just remove the I here. Just think about A here as the Hamiltonian operator for a harmonic oscillator. So we know that's equal to h bar omega, right? And then we have this number operator N here. You should also have a half here. So this should also, so this basically just denote an energy of a harmonic oscillator. And then what's going on here is, if we put this together, so this lambda k is basically this h bar, let's call it omega k here. So suppose, A acting on per psi k here is equal to, say, h bar omega k. I'm just going to remove the 1/2 here for simplicity. So this basically denotes that each of the per psi k state has an energy of h bar omega k. And then when you do the sum of the A here, you're basically summing over the total energy. So that's basically given by h bar omega and k, and you sum over different k's. So it's like you have k different harmonic oscillator, and each one of them has an energy of h bar omega k. And then when you sum over them, that's what you get. Yeah, question, Connor?
Yeah, was that Fock basis you used above, was that already in, was that basis already like the eigenstates of the operator you used on it?
Yeah, in this particular case, if I'm using the number operator, yeah, so then this per psi k is already the eigenstates. Usually in this case, we always want to use the eigenbasis for the operator A because you can actually see that this makes this many-body operator actually diagonal, right? Because it acts on the basis state and you end up with the same basis state. So it's an eigenstate, you're right, but it's a many-body eigenstate. Right. So in this basis, you can see that this curly operator A here is basically diagonal in the sense that it doesn't actually change the basis state we're talking about. Any other questions? All right. So the next part, we're going to make things a little bit more complicated. As Connor just says, we can use the eigenstate for the operator A here, but we may not need to use that, right? We can also use a different basis, right? And that makes things a little bit more complicated. And this is also something related to the change of basis we just talked about. So what if we use a different basis for the single particle Hilbert space? So suppose we actually use a basis phi L for the single particle Hilbert space. So in this case, this operator A here will not have this relation we just talked about. And then in this case, we have to basically do the basis transformation. So what we're going to do is, remember the basis transformation we're talking about, right? We can actually, so let me just rewrite this formula down here. So we have AL dagger is equal to sum over K, UKL, and then we have the CK. Right, so this is the basis transformation between the AL and CK. And the CK here are still the creation operators for the particle in the eigenstate of A, which is given by psi K. In this case, we know that the A is just equal to sum over K, NK lambda K. And this can also be written as lambda K, CK dagger, CK. Right, because NK here is a number operator. That is just equal to the CK dagger, CK. So this is kind of in the basis that makes the operator, this many-body operator diagonal. It's just a sum of that. But now we are using a change of basis, so we can actually see how we can represent this curly A here using these creation and annihilation operators in a different basis. So here we basically want to change the CKs to AL. And for that, we can't use this directly because this is like if you have the A's, you can write it in the C. So we need to do an inverse transformation. So we need to do an inverse transformation here. And because U is a unitary operator, doing the inverse transformation is relatively easy. So what we're going to do is to just change the summation to L, and then we will have basically the inverse of this. So it's going to be looking like U, I think it's ULK, UKL, star, AL. Because the unitary, the inverse of the unitary is actually equal to U dagger. So with this, what we're basically going to do is to change the basis, and you're going to end up with a different combination. So we're going to plug it here. So we have lambda K, and then we have sum over L, UKL star, AL dagger. So we basically use this equation here. So the CK dagger is replaced by this. And we also have CK here, which is just the Hermitian conjugate of this. So this becomes, so I need to use the L prime here because L is a dummy variable. So let's just do UKL prime here. And there's no complex conjugate because I'm using a Hermitian conjugate. So this becomes AL. Right, so I need to do this. So you can see that I have three sums. I have a sum over L, I have a sum over L prime, but I also have a sum over K. But the sum over K can be performed first because the sum over K is just over a bunch of numbers, right? You have UKL star and UKL prime. So I can first sum over K, and then I can call that whole coefficient just some number. I can call it A, L, L prime. And then this becomes AL dagger, AL prime. And here this A, L, L prime is exactly the sum over K. I have lambda K, UKL star, UK, L prime. And this might look a little bit complicated to you, but this is actually just the matrix representation of operator A in the new basis phi L. The lambda k's are eigenvalues of A. This is kind of like we know in the eigenbasis of A is a diagonal matrix made of lambda k. But if you look at a different basis phi L, this is what the operator A looks like. So this is again undergraduate quantum mechanics. So this is just a matrix representation of the operator A in the new basis. And this equation here is actually the general equation for representing a many-body. It's a single body operator, but it's in a many-body system. So this is the recipe you need to remember. And it's actually not hard to remember. So what it does is you first choose some single particle basis state. So here we call it phi of L, right? This is some single particle basis states. And then you define the creation and annihilation operator for these basis state, right? AL dagger denotes the creation of a particle in the eigenstate phi L. and then you write the matrix element of your operator A, right, in this basis, and then you do AL dagger AL prime. So this is less obvious physically than the diagonal form, right? I'm going to highlight this one. So this one is a little bit easier to understand because it's diagonal in the sense that you can see that there's a single sum in K, but this has a double sum, and you got like a matrix element. And in the case of where the ALL prime is already diagonal, like in its own basis, it basically just reduces to a single sum over lambda K, which is diagonal matrix element. In that case, you basically just get the creation and annihilation operators with the same type. So it becomes C dagger C. And C dagger C makes intuitive sense because in this case, it just denotes the number of particles in that eigenstate. So the one in yellow is intuitive to understand because we are actually in the eigenbasis of the operator. But the one in the bottom is what happens if you choose an arbitrary basis for the single particle. So you will get this quadratic form. So later on, we're going to talk about, this quadratic form actually appears in a lot of different cases physically. So whenever you see an operator that is written in a quadratic form of this creation and annihilation operator in this pair, it actually turns out that this particle, this particular operator must be a single body operator. It's a single body operator, it's a single particle operator in a many particle system, in the sense that it's a sum of operator that only concerns the property of each individual one. So as long as you see this form, it actually can be reduced to a single particle single particle operator, especially by the change of basis to its own eigenbasis. Yep, question.
What is the AL prime conceptually? Just like the.
It's a matrix element, so it's basically just a matrix element of the operator in an arbitrary basis.
Okay. So
yeah.
The prime denotes the next.
Yeah, it's just the row and column index, right? Yep. Okay, so I want to show you an example. So this is kind of all very general. So what about we look at this particular example of a Hamiltonian. So we'll give an example here, sorry. So let's talk about a particular example of this. So we have a Hamiltonian. So whenever I use this curly, it denotes that this is actually a many-body Hamiltonian. So it's a Hamiltonian, or it's an operator that represents the energy of n identical particles. And this particular Hamiltonian is given by the sum over all the x and x prime, which kind of plays the role of the of the L and L prime there. And then we have some matrix element. So I'm just going to denote it by H, X, X prime, and then I have AX dagger, AX prime. Right, and according to what we just said, this is actually the matrix element of H in some basis. And this particular basis, we can just call it the position basis. So we're actually using the position basis X here for this single part, for these particles. For a single particle, here we choose the position basis as the basis of the Hilbert space. And this HXX prime is just going to be X, X, H, and X prime. So here H is a Hamiltonian. Suppose you just have one particle in the system. You can always define its Hamiltonian, right? It's like a one-dimensional particle. And then you can basically find the matrix element of this Hamiltonian in this X and X prime. So that's the matrix element of it. We do the inner product. And then you can put a many-body Hamiltonian in this form. So the physical interpretation of this is this term creates a particle in position x, and then it removes a particle at position x prime. Right? So then you have some coefficient given by that matrix element. So this type of Hamiltonian has a particular physical meaning. So this type is called a hopping term. Sometimes also called hopping energy. And people typically just call this hopping. So what that means is the particle for this particular term, it actually means where the particle is going from the position x prime to the position x, right? Because you are removing a particle at x prime and creating one at x. So physically, that means is a particle can actually move from x prime to x. And then the coefficient here kind of denote the energy of that process, right? So later on, we're going to show that this hopping energy is kind of related to the kinetic energy of the particle, right? If you think about the particles are moving in space, it's a kinetic energy of that allows you to move from one position to the other. So this particular matrix element actually, is related to how much kinetic energy. It's kind of related to the p squared over 2m we're talking about. But this is like a second quantization way to write this operator down. And this is much more compact because you never need to worry about all these tensor product with identities on the other particles like what we did on the top there. We basically just rewrite everything in terms of creation and annihilation operator. Yeah, question, Bora?
Yeah, when there are different sites, I get how it's hopping between them.
Yeah.
But when it's on the same site, what does that mean?
On the same side, yeah, so that's a good question. If it's on the same side, you just set x equals to x prime, and then a dagger x, ax prime just becomes the number of particle in the position, in the particle x, right? So typically, if you're looking at the hopping energy, we typically set x not equal to x prime, and then we will have another term, which is, of course, basically x equals to x prime, and then we have nx, and typically this will have some other term, we typically call it mu x. And this other term here is just like diagonal, so it's just proportional to the number of particles at each position. And this term also has a different name, it's called the chemical potential. We'll explain this later on, so this is just to give you a brief idea. And this type of Hamiltonian is very common on a lattice or for interacting electrons or for other, for example, if you have optical lattice, you trap a lot of neutral atoms in there, you will typically get a Hamiltonian like this. Yeah, that's a good one. Yeah, x can be equal to x prime. And here I'm using a sum here. In principle, if x is a continuous variable, I should use the integration, but I'm using sum just to make it easier to understand. And the other reason is later on we're going to talk about a lattice. So basically, these particles' position is actually discrete. So you can't actually, the particle can't appear in any position. It's always at a lattice, so it can only be in some discrete position. Right. So then this is the reason why I'm using sum instead of integral. Any other questions? Okay, so as I just said, we're going to talk about what this actually means for a lattice. So suppose we have a lattice in 1D. So I'm just going to draw a lattice potential here. And then we have some particles here, which are basically just trapped in any of the potential bottom. So this is not a good drawing. So usually the potential is pretty narrow, so the particle is well confined at pretty much around that position. So in this case, the particles can't be at any position, but only at these particular bottom of the potential well, and we can just denote this by some lattice side index. So suppose this is lattice side 1, 2, 3 all the way, and then we can basically just label these x by the lattice side index. So in this case, instead of writing this as ax dagger ax prime, I can actually write it as just ai dagger aj. So this basically denotes that I create a particle at lattice side I. Right. Because I have a lattice, then the particles are basically going to be placed exactly at the lattice positions. And this is a very common situation for real materials, right? If you have a crystal, then you're going to form a lattice. And then the electrons can basically only be positioned at exactly those lattice sites. Anywhere between the lattice sites, you will have negligible probability to find an electron there, just because you have some potential there, right? So in this case, I can rewrite this Hamiltonian as just a sum over I and j. So here I'm going to still assume I is not equal to j. So then I have some coefficient. So here I just call it hxx prime. So this one I just call it some coefficient of tij. I use t here just because it's used in the literature often as well. So then I have ai dagger aj. And if you look at what the tij is, so we can kind of just do this this inner product here. So this x and x prime is no longer the position basis because here we have the lattice, right? So the x and x prime can only be some particular one. So I'm just going to call it phi I h and phi j of x dx. And each of these phi I x is basically an eigenstate or eigenfunction of the particle at a position at a particular lattice side I, right? If the particle is at a particular lattice side I, you are basically going to get a wave function that looks something like this, right? It's going to be peaked somewhere here. Oops. You're going to get a wave function that is basically peaked at a particular lattice side. And this wave function has a particular name. It's called the Wannier. We'll just call it the Wannier function. So whenever you have a lattice, then your basis becomes discrete, right? Because instead of having just these position basis x, where the wave function will just be a delta function at any arbitrary position x, now you have this Wannier function, which is kind of like a delta function centered at each lattice position, right? But because it's discrete, and also you can't get a perfect delta function, no matter how how tight your potential is. Usually it's some kind of localized wave function, but it's not exactly a delta function. It has a certain width, and people call this Wannier function. You can exactly calculate them. And then these phi i's, if you want to calculate these coefficients Tij, we basically just do this integral. This is just how you find the matrix element of your Hamiltonian in quantum mechanics. But here we're using the wave function representation, so we're doing the integral here, right? So that gives you this coefficient Tij. Okay, so so the other approximation we can make is so typically in a real lattice, these wave functions, basically these phi i's and phi j's, they have very little overlap if I and j are more than one lattice side apart. So here I'm just going to use a different color here. So if you have this Wannier function for side I, and you have another one for the side next by, so these two will still have some overlap, right? Because they're just next to each other. And what the overlap means is this integration will usually be non-zero. But if you look at a side which is further apart, for example, let me use a different color here. I have another lattice, say 3 lattice sides apart. So I'm looking at this one. And then the wave function is going to be a localized wave function here, right? And if you look at the overlap between the black one and the blue one here, only the tails will overlap, but that overlap is tiny. And because of that, if you look at this integration here, because the psi I and psi j, right, the product of them are basically 0, right? Almost anywhere, just because of their localization, then this Tij here is basically approximately equal to 0, unless I and j are neighbors. Right. So unless I and j are neighbors, we can pretty much ignore this this overlap integration, which means this coefficient basically becomes a literal 0. And because of that, we can replace this by just the neighboring summations. So this is typically denoted by this notation where you put an angled bracket. It's kind of like the cat-rod notation, but it's actually not. So this I and j just denote that I and j are neighbors. The neighbors on the lattice. So in 1D, we typically just write it as a single summation of j equals to I plus 1. Right. In 2D, it's more complicated, but the approximation is that we assume that the Tij, the coefficient, is only non-zero when I and j are neighbors. In 1D, it's just I and I plus 1. And this model has a pretty famous name. It's called the tight binding model. So this is the simplest model in condensed matter physics that models the band structure of electrons in a solid. Question caller.
Why does the Hamiltonian not have a diagonal elements?
I'll come to that. Yeah, the diagonal elements, yeah, you can't have that. but this is the more important one. Yeah, you're right. So you can add a diagonal part. Sum of I, so we can just call it mu I, and then ni. Ni is the same as ai diagonal ai. So it's a number operator. And that term is typically called the chemical potential term. I'll explain why that's what that means just in a second. So this is called the tight binding model. And why it's called the tight binding? The tight binding is kind of related to the fact that the electrons can only hop to the neighboring lattice sites, just because this coefficient here is only between the neighboring sites. So if you put the electrons on a lattice, which is like a real solid crystal, then electrons can only hop between the neighboring sites. So that's usually called the tight binding approximation. Like you only assume the electrons can hop to the neighboring site. And this particular term here exactly represents the hopping of the electrons on the lattice. And for this second term, so this term here is diagonal, and usually this term does not correspond to any kinetic energy, because you can assume that it's something more close to a potential energy, right? So it doesn't represent the particles hopping. It's just like if you have Ni particles on side I, you will gain an energy that is equal to sum over mu I times Ni. So it basically means if you want to add a particle at lattice side I, you have to pay an energy which is mu I, right? And typically, for the uniform lattice, we're going to assume that these mu i's are the same. So typically, we're just going to have this term that looks like a mu sum over I, Ni. Suppose it's a uniform lattice, then it's the same thing. And I'm not sure if everybody learns the concept of chemical potential in either your chemistry class or your classical thermal physics class, but the chemical potential, the definition of that, the chemical potential is basically the energy you need to pay if you add one particle to the system. So that's the concept for chemical potential. So it's an energy for adding one more particle. And it could be different, but usually if you have a uniform lattice, then you can add the particles on any side, and it costs you the same energy. So that's the definition of chemical potential. Your question.
Did you say they could only hop if they were neighbors?
Yeah, in this, described by this Hamiltonian, yes. They can only hop if they are the neighbors. So it's called the tight binding approximation. But of course, you can do a second order process. You can first hop to the neighboring site, and then you hop to the next one. But it's a second order process, which basically means it will happen with slower, much smaller probability. Right? If you have a probability of p to hop to the next site, then you will have a probability of p squared to hop to the next site. Right? Of course, you can also have a Hamiltonian that violates this tight binding approximation. You can actually have the Tij not equal to 0 when I and j are two sides apart. We'll talk about those briefly later on, but for now, this is a model that's used the most. We just assume the particles are only hopping to the neighboring sites. Yeah, so this tight bounding model is quite simple. You only have two terms. One is this quadratic term. The other one is a diagonal term. But it's actually the premise of many important models, much more realistic models, incorporating, for example, electron interactions. So later on, we're going to talk about the Hubbard model. Which is built upon this tight binding model. So you're going to add an extra term that represents the interactions between the electrons. And this Hubbard model is very famous because if you model this for electrons in the solid, people believe that's actually the underlying model for superconductors, and even some of the high temperature superconductors. So when we talk about this quantum simulation, I showed you this video, and then we know that everybody is searching for this high temperature superconductor, and that's a very important application of quantum simulation. So how do you know that if you're doing quantum simulation? You actually don't need to simulate a real material. You just simulate this Hubbard model, which is basically this Hamiltonian with some extra interaction term. We're going to probably talk about that in the next class. And if you can simulate that with a different type of system, for example, with cold atoms in optical lattice, and you can find the correct regime of the parameters in your Hamiltonian, for example, your Tij values and also interaction strength, then you may be able to find the regime where this whole material is superconducting even at room temperature. So there's actually a very big grant by DARPA, which is one of the funding agencies by the Department of Defense. I was actually involved when I was a PhD student. To be exact, my advisor is involved in that big project, and they spent like I think it's several, almost 100 million on that. Basically by exploring this direction. I think they get some positive result. It's still not yet that yet, but at least we have these fermionic code adding experiment that can simulate the Hubbard model. So we made some big progress in that. All right, so I'm running out of time here. I'm just going to stop here. In the next class, we're going to keep talking about how we represent two particle operators in second quantization form.